In previous lesson, we learned the central limit theorem for the sample mean. The distribution of sample mean is approximately normally distributed when the sample size is large. This also holds true when we consider the sum of independent identically distributed random variables. So the setting is similar to the previous case. We have independent i.i.d. samples, so a simple random sample from a population. That's denoted the observed sample values as y1, y2 up to yn. And here we consider the sum of the yi. This summation also changes when we have a different sample collected. In one sample, you have a computed value, and if you move on to a next sample from a different experiment, you could end up having different value. So the summation is also a random variable. This random variable would have approximately normal distribution with the mean equals n times the population mean and the variance equal to n times the population variance. Therefore, the standard deviation would be the square root of n times the standard deviation from the population. And here we also have the n need to be large. So this distribution is approximate when n is large. And when n is when the population distribution is normal, that means that y1, y2 up to yn has normal distribution. In that case, this summation would be normally distributed regardless of how big is the sample size. In other words, if the population is normal here, population is normal, like you're given the condition that the observed data y1, y2 up to yn seems to be reasonable to be from a normal distribution. In that case, when you have different samples collected, you compute the sum of these yi's. The sum will be will have exactly normal distribution. And the mean and the standard deviations will follow these the formulas in these two rows. And these do not depend on the population distribution. The mean and the standard deviation part will hold regardless of what is the population distribution and what is the sample size. Let's look at an example. A bridge holds up to 25 cars, and it's known that the weight of individual cars is normally distributed with a mean of 2,100 pounds and the standard deviation of 500 pounds. The maximum load for the bridge is designed to be 60,000 pounds. What's the probability that a full load of cars will exceed the design limit? So here we know the total allowable weight is 60,000, and these cars the weight of the cars are random variables. They are normally distributed. So we're considering 25 cars. So you can think of it as we have x1, x2 up to x25. And these x25 are the weight of 25 cars. And we want to consider the total weight of all 25 cars randomly passing through the bridge. And what's the probability that the total weight would exceed 60,000 pounds? So here we want to consider S25 greater than 60,000 pounds. So we needed the mean and the standard deviation of the S25. Since we know the population distribution is normal and the standard deviation is 2,100 and standard deviation for the population is 500, so we know this S25 would have normal distribution and the mean is equal to 25 times the one of the mean. And standard deviation, it would be square root of 25 times the population standard deviation. That gives us 5 times sigma, which is this much. Once we know the mean and the standard deviation, we can simply compute the p-value or the probability of greater than 60,000. And this is done by the 1 minus p norm with the 60,000. And then we put the mean here. This part is the mean. And this part is the standard deviation of the variable. That will give us the probability. In this case, 0.0013 5, so it's a very small probability that the total weight of 25 cars will exceed the design limit. This next example is about the weight of tomatoes. We're looking at the medium-sized tomatoes in a grocery store, and that's a random variable with a mean of 6 ounces and standard deviation of 1.2 ounces. Suppose we randomly select 5 tomatoes in a bag. The mean weight is a random variable. What's the mean and standard deviation of it? So this is talking about the mean weight of 5 tomatoes. So in other words, this is the sample mean. And this sample mean depends on which 5 tomatoes that you take from the store, put it into the bag. So that's a random variable. And here, this is asking about the mean and the standard deviation. This is the parameter for the distribution of the sample mean. So we know that the mean is equal to the population mean. So we'll write the X bar has a mean equal to a population mean mu equal to 6. And the standard deviation equal to the standard deviation sigma divided by the square root, multiply by this, excuse me here. Since we're not looking at the X bar, yeah, it is X bar, okay. So for the X bar, mean has the same mean as the population mean, and standard deviation is equal to sigma over square root of n. So in this case, it would be 1.2 divided by square root of 5. The next question, total weight of the 5 tomatoes. When we look at the total, this time, again, the mean and standard deviation, mean would be equal to 5 times the mean of 1 tomato. So it's 5 times 6 here. This is 5 times 6 give the mean. And the standard deviation would be square root of 5 times the standard deviation. So here gives the standard deviation. And next question, what's the chance that the total weight of the 5 tomatoes is over 2 pounds? So this is asking about the S5 is greater than 2 pounds. 2 pounds in this case, since the mean and the standard deviations are given in ounces, so our computation need to convert the 2 pounds to 32 ounces. So we want S5 greater than 32 ounces. For this probability in R, we can compute it with 1 minus P norm, and we put 32 here, and the mean is 30. That's 5 by 6, and the standard deviation is that the square root of 5 times 1.2. So that will give us the probability. In this case, we get number 0.228. So there's 22.8% of the chance that the 5 tomatoes will be over 2 pounds. Okay, next let's try to apply the central limit theorem for the sum to a situation in a binomial experiment. Before we look at the binomial, let's first consider the case that we have just 2 possible outcomes. And there are many of the real-life situations we see 2 outcomes. For example, when you flip a coin, you might see the head or tail. So the head and tail are the 2 possible outcomes. Another one, consider the Democratic versus Republican Party, whether the president is in Democratic or Republican Party. Also 2 outcomes. And male, female, win or loss, success or failure, a product being defective or non-defective, and so on. And even if you have multiple outcomes, let's say originally you have consider political affiliations, there could be Democratic, Republican, and Independent Party. But if you are only interested in study about the proportion or probability of falling into one category, say Democratic Party, then you can combine the other 2 categories together. So it becomes Democratic versus non-Democratic. That still can be studied in the 2 outcome situation. Whenever we have these 2 outcome situation, when we have just one of the subject or object being selected, we see what's the outcome. If it's the outcome of the category we're interested, for example, success, failure, if we randomly select one and it is a success, In that case, we record a value of 1. And if the result is a failure, we record a value of 0. This kind, recording the value of 1 or 0, then we call it a Bernoulli experiment. So Bernoulli simply refers to that the experiment will result in the two possible outcomes, the 0 and the 1. That's Bernoulli. It's simply just only having one experiment. In the experiment has only one trial, and this one trial will give us the outcome in either 1 or 0. The next one is called a binomial experiment. In this case, we're considering multiple Bernoulli experiment, and in fact, we're considering fixed number of those Bernoulli trials, and each one of the Bernoulli trials give us the success or failure, so 1 or 0, but we are interested in the total number of ones out of a fixed number of trials, and assume that these different trials are independent. Then we have this binomial experiment. So binomial is simply the number of ones in the fixed number of trials. This is the binomial. When we write the 0 or 1 for the Bernoulli experiment, then this outcome of 0 or 1 becomes the possible value, and we say that outcome is a Bernoulli random variable. And there are many situations that we encounter Bernoulli random variable. For example, consider this question: do you favor the development of solar, the policy of allowing solar energy in all states? This is one question. And for this question, if you ask any person, this person would respond yes or no. That's suppose we do not, we rule out the other third opinion. Or if we only care about what proportion of people are in favor of this development. For those in favor, we record 1, and those not recorded as 0. Okay. So this would be a Bernoulli experiment if we look at this one person's opinion. And when we look at many persons' opinion, like for example, we select 10 persons and we ask each person's opinion, then what we have is going to be a binomial experiment, binomial random variable. How many out of 10 are in favor of this policy? Then that's a binomial. So next one example, Gallup and Harris polls are examples of the sampling of 0-1 populations. People are surveyed and their opinions are recorded based on sample responses. They estimate the proportion of people in the population who favor some particular issue or possess some particular characteristics. This is a pretty common kind, like they do political surveys and so on. Similar surveys are conducted in biological sciences, engineering, business, but they might be called experiment rather than polls. For example, experiments are conducted to determine the effect of new drugs on small animals, such as rats or mice, and before proceeding to the large animals, and eventually they will apply to humans. When the experimenter record whether the drug is effective or not on each of the participants, so when we simply look at the outcome from one participant, it's either effective or not effective. When it's effective, then we record it as 1, and not effective, record as 0. So we have a Bernoulli random variable. So there are more examples here, like Kansas City Bank checking plus customers, they would receive this higher interest rate, like 1.5 or APY, if they meet some conditions. These conditions include at least 10 of the transactions using debit card and at least 1 ACH transactions. And if all these conditions are met, they are going to get this higher interest rate. If they don't, if any of the conditions is not met, then a low interest rate will be applied. So for randomly selected customer, whether this customer qualified for the higher interest rate, That's a Bernoulli random variable. Next example, for each student in a class, whether the student had close contact with a person who has found to have positive coronavirus, who was recently infected with the coronavirus. And if it's a close contact, we record as 1, otherwise record as 0. So for any randomly selected person, we would have a Bernoulli random variable. So the next example, a product of a specific type is classified as class 1, 2, 3 based on its fire resistance level. For a randomly selected product of this type, record whether it's not of class 1. So the indicator variable of class 1 or not of a class 1, that's a Bernoulli random variable. So this is the kind that originally we have 3 categories, 1, 2, and 3. But we care about one of them and combine the other 2 together so that still any of those randomly selected belongs to one class, the one of interest or not of interest. So that becomes the Bernoulli random variable. Okay, the next one, for 50 patients with certain disease, a new medication is given to each patient in the study. In the end of the study, whether the person is recover or not. For this one, each person, whether recover or not recover, that will be a Bernoulli random variable. The mean and standard deviation of Bernoulli random variable. For Bernoulli random variables, there are only 2 possible values, the 0 and the 1. And when we learn about the mean, we know that the mean is for a random variable is defined as the average of all possible values, the basically weighted average of all possible values. Let's suppose that we have the probability of 1 given by p. This p is the proportion of 1, okay? Or call it the success probability. And the probability of 0 would be 1 minus p. And these are the 2 possible values, 0 and the 1. The 1 has probability of p, the 0 has probability of 1 minus p. And when we consider the weighted average of 0 and 1 together, this gives us the mean. The mean of a Bernoulli random variable, once we finish the computation, we see it's equal to p. That's the mean of Bernoulli random variable. We also say it's expected value of Bernoulli random variable is equal to the success probability. The standard deviation of a Bernoulli random variable. For Bernoulli, again, when we compute a standard deviation is defined as the square root of variance. And the variance is the squared deviation variance, okay, is squared average weighted squared deviation of all possible values. And the weight is again is the probability. So we have a 0 as a possible value, and the mean is p. So squared deviation from the mean, 0 minus p squared, and this is for value 0. We need to multiply its probability. And we also have the value of 1, and that 1 also minus the p, and multiply the probability of 1. Probability of 1 is equal to p. So let's simplify this one. In the end, what do we get? The first one is a p squared times 1 minus p. The second one is p times 1 minus p squared. So we take out the p and 1 minus p together, and what's left is a p plus the 1 minus p, and which is the 1. So eventually what we get is p times 1 minus p that give us a variance. Okay. So what I wrote here, this part, this is the probability of 0, probability of x to take value 0. Okay, and this is the 0 minus the mean of it. And the next one is 1 minus the mean of the variable and times the probability of 1. So this gives us the variance formula p times 1 minus p. This derivation is not required, but you do need to remember the mean and the standard deviation of the Bernoulli random variable, so that later on you can use it when we need it. So for okay, this gives us the calculation of the variance, and if we take the square root, we will get the standard deviation, which is p times 1 minus p. Okay. Here are some examples to ask you to give the mean and the standard deviation of the variable x. The first question, a physician knows the probability that a patient will recover from a certain disease 0.25 when treated with the current medication. Let x be the indicator variable of whether a patient recover or not after treated with the current medication. What's the mean of x and standard deviation of x? So here, our x is just indicator of recover or not. If indicator variable always means that it's either 1 or 0. So in this case, if a patient recover, the x is equal to 1. So x is 1 or 0 if the patient recover. Otherwise. So it is a Bernoulli random variable. And for Bernoulli random variable, we have the mean of x equal to the proportion. So in this case, is the 0.25. And the standard deviation is equal to the square root of the p and times the 1 minus p. 1 minus 0.25. Take the square root. Okay. The next one, suppose 50% of a population is overweight. A person is randomly selected. Let x be the number of person that's overweight. Again, here we are having just one person randomly selected, and we are looking at x be the number of person that's overweight. Since we only have one person, this one person is either overweight or not overweight, so the number would be either 1 or 0. And for 1 or 0, the mean of that for Bernoulli random variable mean is equal to the proportion 0.5. And standard deviation will be the square root of this p times 1 minus p. The next one, the quality of a computer disk is measured by the number of missing pulses. For a certain brand of disk, 10% are generally found to contain at least one missing pulse. So here's the proportion for the population, 10% to have at least one missing pulse. That x represents the number of disks containing at least one missing pulse. And this is talking about in one randomly selected disk. So it's one disk, and we are looking at this one disk, whether it contains at least one missing pulse or not. So x is again Bernoulli distribution is a Bernoulli random variable. The mean of x is equal to that proportion 0.1, and the standard deviation would be equal to the square root 0.1 times the 0.9. So these are the examples. Next, let's move on to the binomial distribution. A binomial random variable simply is the sum of a fixed number of Bernoulli random variables. When we say we have a binomial experiment, if the following properties are satisfied. The one thing is that we have fixed number of Bernoulli trials, fixed number of trials, and these trials are identical. The next one is each of the trial has only 2 possible outcomes, and these 2 outcomes we can always label it as, for example, success or failure. And later on, whenever I talk about the binomial probability, I call it the success probability. Even though in the real practice, this category, whatever category you are interested in, that proportion is for that category. Probability of success on a single trial remains to be a constant p from trial to trial. That does not change. This is a constant success probability. The next one is the trials are independent. the outcome of a trial do not influence the outcome of another trial. So that's independent trials. And what we care is the number of successes obtained from the n trials. Then this y is a binomial random variable. So number of successes from a fixed number of Bernoulli trials, that's a binomial random variable. Here's one example. For this example, we're looking at this Manhattan in New York, attorney Lawrence he was the patient 0 after testing positive in the coronavirus case in New York City. And his family members, friends, and co-workers in his law firm and many clients were in direct contact with him. And so there are a total at least 37 of other confirmed cases in New York was connected to him. For this one, we want to look at the number of people who received a positive test after contact with this lawyer. And that's a random variable. Does it satisfy the property of binomial experiment? So we'll try to check each of those characteristics of the binomial experiment. One thing is, does it contain fixed number of trials? So for this case, the number of contacts with this attorney, that's 37, and that's fixed number of contacts. And assuming that, this is a fixed number of contacts. And as far as whether they are identical trials, let's say, suppose that these approximately, if each person had long enough exposure or contact with him, then has the same chance of being affected, then we believe that would be identical trials. But this has some assumption there. Next one, did each trial result in one of the two outcomes? Yes, that's correct. Each person is either going to be positive or negative after the contact. Next one, was the probability of success the same from trial to trial? This again will depend on the exposure and also the immune system of the person. But I guess here we're talking about the probability of whether the test is being positive or negative, assuming that this at the early stage, the coronavirus was highly contagious. So was the trials independent? Yes, the outcomes of one screening test was unaffected by the outcomes of other screening tests. So they are independent. Next one, was the random variable of interest to the experimenter the number of successes among all those tests? So the number of direct contacts who obtained a positive result was of interest. So the random variable is interest. It's the number of those that have positive results. So yes. So roughly, we would say that this could use the binomial distribution to describe the number of patients who get positive result from all those that had the direct contact with the lawyer. So this is just an approximate situation. In real life situations, there are many of the cases that a binomial experiment would be an approximation. It's not exactly following that, but the binomial experiment would provide a pretty good approximation or good fit to that. One of the situations is that, say, in this binomial experiment, when we try to randomly select one person out of the population, this one person, when we select out of the population, we are really assuming that there are infinite many of the members in the population for us to select from. And when we do that, each person has equal chance of being selected. But if we have a finite population, then after you select one person and assuming that person cannot be selected again, and you select the next person, then the chance of the next person being selected compared to the first person being selected may not be exactly the same when we have a finite small population. But if the population size is large enough, then the binomial would still provide a good approximation for the model. The probability distribution of binomial random variable is given by this formula. So this is basically considering all those that are successes out of n trials. Let's say the number of successes is y, and the number of failures would be n minus y. So each of the successes we have the probability of p, and there are y of those, so p to the power of y. And we have n minus y of the failures. And we consider all of those that will be n 1 minus p to the power of n minus y. And beyond that, for y successes, these y successes could be, for example, these are the total of n of them. And let's say the y are referring to the 3. It could be the first 3, or it could be the second 3, or it could be the 1 and the third and the fifth. So selecting 3 out of n, and as long as we are having 3 of those to have success, all of those will give us the same probability. That's why here we have n choose y. That's the number of combinations of choosing y out of n of these trials to have the success. So this is the binomial probability. This probability for this combination number, if the n is small, it's pretty easy to calculate. But if n is large, then the computation could be pretty difficult. Particularly, it's going. For example, if n is 100, the calculation of the 100 factorial will be difficult. Factorial, like n factorial, simply means that the product of 1, 2, 3, 4 up to n. And imagine if you have 100 numbers being multiplied together, very likely that the computer would not allow that much of the many digits to be there. So that's for this probability. And for this probability in R, we can use the D, binom, the D for density, binom for the binomial. And with this one, you would need to feed the value y, and you also feed the number of trials and also the success probability to this command. Just a second, let me try to confirm. So we are going to provide the n here and the p there. So generally the formula is this first one is the y, and the second one, this is the number of trials, or the size, number of trials, or call it the size. Okay, and this p is the probability part, PROB. When we provide this, then we will get the probability distribution. Here's an example just to illustrate about the calculation for the binomial random variable. Suppose we are considering the production line, and we're looking at the motor housings. 5% of those have cosmetic defects, and the quality control manager randomly selects 4 housings from the production line, and out of the 4, we want to see how many of them have cosmetic defect. When we try to calculate the probabilities, we can consider all possible values of the x. The 4 housings are selected. The number of defective ones could be 0, 1, like 0 is one possibility, 1 and 2, and so on. And for the 0, that is straightforward. So all of them have to be good housings. So for the 0, that means all 4 of them are good. For 1, If X is 1, that means that out of the 4 housings selected, one of them is defective. It could be the first one being defective, like this case, the other 3 are good. Or it could be the second one being defective, others are good. Or it could be the third one defective, all the rest are good, and so on. So for those that are having one housing defective, well, basically the number of those entries would be 4, choose 1. So that gives the probability of 1. Similarly for all the others, and the computation would be done similarly. And what we have listed here are those probability of the 0, 1, 2, and so on. And if we type them together, the 0, 1, 2, 3, 4 would give us this probability distribution. Here is the probability distribution for this the number of defective housings out of the 4. As we look at it, the probability is the 5%. That's defective 5% have the cosmetic defect. So out of the 4 housings, the number of no defect, the number of housings with no defect is actually very high, 0.814. And the number of 1 defective ones is 0.17. And for the number of defective housings being 2, 3, or 4, they have very low probability. And the question here, what's the probability that at least 2 of the housings will have cosmetic defect? So at least 2, that would refer to the 2, 3, and 4, these 3 situations. So we simply just add up the probabilities for 2 and 3 and the 4. So that's the probability related to this binomial. For this computation, we do not have to manually compute. Instead, we can compute in R directly. Probability of X greater or equal to 2. We can use so that means it contains the 2, the 3, the 4. Since we have the number of trials equals 4, possible outcomes are those 2, 3, and 4. That's what we want. So we basically rule out the ones below 2. So we use 1 minus the probability of X less than 2. And for the less than 2, that's either the 0 or the 1. And we use the P binom, P-B-I-N-O-M, and with the 1 there because it's less than 2. We cannot have 2 because if we put 2, that means less than equal to 2. So we have to use the 1 minus the P binom. We put the 1 there, we have 4 trials, and we put the success probability 0.05. Okay. This is the kind that I preferred, but if you are also comfortable to use this additional input variable lower to specify, you can also use the other way. So that's about the computation of the binomial probability in R. Next example, identifying newborns. After spending 1 hour with the newborns, each mother was blindfolded and nose covered and asked them to choose their child after from 3 sleeping babies by simply feeling the backs of the baby's hands. There are 32 mothers, and out of the 32, 22 of them selected their own newborn. So with the 22, that's close to about 2/3. Does it really say that the mothers do not make random guess? Because if they randomly guess, then which one is their baby out of the 3, it's 1 out of 3 chance, 33% of chance will find their baby. But here we see that more than 2/3 of the mothers identified their own newborn. So here, let's use the binomial probability to calculate what's the chance of the mother select their own baby. What's the chance of observing 22 or more of the mothers select their own baby out of the 32 mothers. So with n equals 32, what we have if mothers do random guess, if they do random guess. So we have success probability P is 1/3. Then the X follows the binomial. So X here has a binomial and the number of trials with n equals 32 and p equals 1/3. So these are the parameters, 32 and 1/3. We want the probability of probability of x greater or equal to 22. And this probability, again, we use 1 minus p binom with the 21 there to exclude the 21 and below. And then we'll put in the number of trials, 32 here, and we also put the success probability 1/3 there. So what we get is the probability of 0.000045, which means if mothers do random guess, then the chance of seeing 22 out of 32 or more than 22, that's going to be extremely low. How low it is much less than 0.01%. So mothers do not randomly guess. They truly have some sort of mechanism to identify their babies. Since the binomial random variables is simply the sum of Bernoulli random variables, then we can easily find the mean to be n times the Bernoulli random variables success probability p. And standard deviation is simply the square root of n times Bernoulli's random variables standard deviation. So this np give us the mean, and np times 1 minus p give us the variance. If we take square root, that give us standard deviation. So n times p1 minus p, that's simply the n times the success probability and times failure probability. For example, in that mother and the newborn example, with p being 1/3, then the mean is 32/3. So on average, out of the 32 mothers, it would be about 10.67 mothers that would find their baby, but we observed 22 of them. Standard deviation is 32 times 1/3 times 2/3, because here's the p. The p is 1/3 here, and this one is the 1 minus p. So when you have them multiplied together, take square root, you have the standard deviation. The last part of this lesson is about the binomial approximation. Approximation to the binomial computation using the normal to approximate. We have already found that if we have a large n, the number of trials being large, then the computation of the factorial could be a problem. For example, say we consider 1,000 voters and determine whether we want to know whether they are in favor of consolidation of city and the county government. And let's say we want to see what's the probability of 460 or fewer favoring the consolidation. And suppose the p is success probability is 0.5. So with this case, we have 1,000 voters and we want to know 460 or less, 460 or fewer favor the consolidation. So basically what we are having is a binomial random variable with n equals 1,000 and success probability 0.5. And we want the probability of y that's equal to 460. If we are going to compute this with the binomial, we will end up having to do a lot of permutations. And it's not possible to compute the 1,000 factorial, even with the computer. So instead of doing that, there is an approximation for this one, because the binomial experiment could be treated as the sum of Bernoulli random variables. So think of the y as the sum of 1,000 Bernoulli variables. And xi is either 1 or 0 if the ith voter favors the consolidation, and 0 otherwise. And these xi's are i.i.d, Bernoulli, and all of them have success probability of 0.5. So we can use the Central Limit Theorem for the summation. Therefore, this y would be approximately normally distributed with mean equal to the n times the mean. And the standard deviation is going to be square root of n times the population standard deviation in population variance. So this case would be the square root of n times the population standard deviation. Okay, p times 1 minus p, and p is 0.5. 1 minus p is also 0.5. And we take square root, and we have sample size 1,000. So that gives us the standard deviation. And for the computation of probability y that's equal to 460, we can directly use now the p norm to compute. We put the 460 there, and then we put the mean of 500, that's from the n times p. And we put our standard deviation there. That will give us the approximated probability. Okay, for this probability, this is an approximation. If n is large, then this probability would be getting closer and closer to normal approximation is getting closer and closer to the binomial. For this example, the binomial, the normal approximation gives us the probability of 0.0057. If we had done it with the binomial, exact probability would be 0.00624. They still have a tiny little bit difference, but I think it's close enough for us to make a judgment of whether this is rare or not. So the normal approximation to that binomial simply says that if we have the binomial random variable, like you have a fixed number of trials, out of those, how many of them are of successes, then that's a binomial random variable. And this binomial random variable can be approximated with normal, with mean of np and standard deviation being square root of n times p and 1 minus p when n is large. What that means is really that we can use the normal to do the computation of probabilities regarding a binomial random variable. So when can we use that? Generally, if n is large, and how large it is, it depends on whether this success probability p is small or not. If p is not very small, so if p is close to 0.5, so center of 0 to 1. If p is close to 0.5, then the distribution of the population is not skewed. In that case, the sum will behave close to normal even for pretty small p. So here's the example. Here's the simulation. When p is 0.2, so p is 0.2, and we computed the sum of 5. So this one is talking about 5. N equals number of trials is 5. Consider the 5 trials. And out of the 5 trials, how many of them give us success? And we repeated the experiment 1,000 times, and we plotted the histogram. You see that with n equals 5 and p equals 0.2, the distribution is kind of skewed. And you increase the number of trials to 10 and 20 and 30 and so on. As you see, when the number of trials increase, it becomes more and more symmetric. That's for the 0.2 being success probability. So with 0.2, we need n to be like 30 or above, right? Like 30 or above. These are pretty good symmetric bell-shaped normal. Next, let's consider p is 0.5. For this case, even with 5 trials, the distribution is pretty symmetric. And for 10, it's also symmetric, with 20 symmetric. So if p is 0.5, you really see that the binomial will behave like normal with not even very large n. The case with the p close to 1, that's similar to the p equals the small value, but just the skew is going to the other side. Like this one, you're seeing the p has a probability of 0.9 for 1, therefore you see more chance of observing the large values. So with 5 trials, you're going to see more of the values close to 1, so binomial from the 5 is skewed, less numbers are this way, okay? So it's skewed to the left. And if we consider the 10 trials, it's still skewed. This is the 10 trials. 20 trials still skewed, 30 and 40. And when you see 50, finally started to be somehow symmetric. So if you see the p close to a point, p close to 0 or p close to 1, in both situations, we need the n to be large, very large, in order for the normal approximation to work well. But for p equals 0.5, the approximation could be pretty good even with smaller n. So this is the summary. Approximation is good using normal when the NP and the n times 1 minus p both exceed 20. So that's the situation when the approximation is good. The next one is if p is small or large, small means close to 0, large means p close to 1, because p is always between 0 and 1, okay? So this small means close to 0, and large means close to 1. If p is close to 0 or close to 1, and in that case, the distribution is skewed, and then the binomial approximation is not going to be good, especially if the NP and n minus p is less than 5. And if that's the case, this could be unsatisfactory. Okay, if that's the case, then we could improve the approximation with the continuity continuity correction. What's that continuity correction? This illustrates that the binomial is really a discrete probability. It only has possible values. For example, in a binomial with number of trials of 20, the possible values are 0, 1, 2, 3, 4, and so on, all those integer values. So like 0, there's a probability. 1, there's a 0, there's a probability. So basically, you'll have all those probabilities for each integer as these bars. That's the binomial. On the other hand, the normal is a smooth curve. For example, let's consider at 5 here. Consider binomial 5. The probability for the binomial are all these bar heights add up together. If we use the normal to approximate all those above the normal, like this part, it was taken into account by this part, right? So those are fine. Similarly, this part and that part was being taken care of. And for this one and that one. But when we consider 5 here, in the binomial, what we really need is up to this point, all of that under this bar being added, all of these. But when we use the normal approximation, we are only getting to this point, getting up to this point. We missed the part, so it's up to this point on the normal curve. We missed this outside part. Because we missed that part, we better just move up by 0.5 to add this part. So that's why when we do the computation using the normal approximation, instead of when we do this probability of less equal to 5, where this x is binomial, we would try to consider the normal, okay, so y less equal to 5, the y is binomial. We would use the normal follows the same mean as the y and the variance of the y. We're going to use the x less equal to 5.5 to approximate it. So we move up a little bit just so that we're going to have this upper part included. So this is the continuity correction. Okay, so we use x less equal to 5.5 to give us the probability, and for the probability of y less equal to 5. Therefore, this computation in R, it will become the p norm 5.5 and the mean and the standard deviation of the binomial. So that's this continuity correction. That's for less than equal to. Similarly, if we want to compute the probability of greater equal to, in that case, for the greater equal to, for example, greater equal to 9, greater equal to 9, okay. If we are considering the greater equal to 9, we are considering all this blue part. But we are approximating with the red part here, red part, using that. So we would miss some part of that, which is on the outside here, and we will try to, sorry, let's see. We want to consider greater equal to 9. Okay, greater equal to 9. When we use the red one to approximate, we missed a part of that. That was on this side. This part was the missed part. So instead of we do the add 0.5 when we consider greater equal to 9, we really need to consider greater equal to this part, this place. So that was the 9 minus 0.5. So for greater equal to a value y greater equal to, we need to use the probability of the binomial greater equal to the y minus 0.5 to approximate. Okay, so that's this continuity correction. So for example here, we consider 100 potential new prescription drugs under clinical test. 20% of those will be licensed for sale. What's the probability that at least 15 out of 100 drugs are eventually licensed? So here we have n equals 100, and we have success probability p equals 0.2. So n is 100, p is 0.2, and we have the number of trials. This number of those that eventually get licensed, that's a random variable y, and this y follows the binomial, with 100 being the number of trials and 0.2 as the success probability. We want the p greater equal to 15. For this one, we first computed the mean of the y and the variance of the y. The mean is equal to np, and variance is equal to np times 1 minus p. So after finished computation, we see the standard deviation becomes the 4. The mean and the variance will be used in the binomial approximation, and this normal approximation to the binomial requires a condition that we know the approximation is good if np and nq are both np times n1 minus p are both at least 20. So in this case, np is 20, n times 1 minus p is 80. Both of them are at least 20. Therefore, the approximation should be fine. So we can use binomial approximation to do the computation. So y greater equal to 15, we use the normal greater equal to 14.5 to compute that. And in normal, we do 1 minus p norm with the 14.5. We put the mean and the standard deviation in it. Okay. So that's the approximation of the probability using normal. For this example, if you compute a binomial, exact probability is 0.919, and the normal approximation is 0.915. They are pretty close. So summary, when we learned the binomial, if the n is very large, and the success probability p is not too small, too close to 0 or not too close to 1, in that case, we can use the normal to approximate the binomial distribution, and probabilities regarding the binomial can use the normal to compute. In particular, if we have np and n times 1 minus p, both are greater or equal to 20, then the approximation is good. If the np or n times 1 minus p is between 5 and 20, generally we would like to do a continuity correction. This correction is to use, if we have a less than equal to for the binomial random variable, we would use an extra 0.5 onto the y when we compute using the normal distribution. On the other hand, when we need to compute the probability of greater or equal to a little y, then we would use y minus 0.5 to account for the little part that's being missed. So that's the continuity correction. This normal approximation to binomial, that's just an application for the central limit theorem. So that's the end of this lesson.